Hello, good evening students. Today we'll discuss about rotational vibrational spectroscopy. Hello, good evening students. Today we'll discuss about rotational vibrational spectroscopy. Rotational vibrational spectroscopy is a branch of molecular spectroscopy concerned with infrared and Raman spectra of molecules in the gas phase. Here, the transitions involving changes in both vibrational and rotational states can be abbreviated as rho vibrational or rho vibrational transitions. So, when such transitions emit or absorb photons, that is from electromagnetic radiation, the frequency will be proportional to the difference in the energy levels that can be detected by certain kinds of spectroscopy. So here, since the changes in rotational energy levels can be typically much smaller than the changes in the vibrational energy levels, so the changes in rotational state are said to be give fine structure to the vibrational spectrum. So, for given vibrational transitions, the same theoretical treatment as for the pure rotational spectroscopy gives the rotational quantum numbers. So, energy levels and the selection rules as well. So, for the linear and spherical top molecules, the rotation lines are found to be simple progressions at both higher and lower frequencies relative to the pure vibration frequency. In symmetric top molecules, the transitions are classified as parallel when the dipole moment change is parallel to the principal axis of the rotation and perpendicular when the change is perpendicular to that axis. So, this vibrational spectroscopy concerns with the molecule in the gaseous phase. There are sequences of quantized rotational levels associated with both the ground and excited vibrational states. So, the spectra are often resolved into lines due to transitions from one rotational level in the ground vibrational state to one rotational level in the vibrationally excited state. So, these lines corresponding to the given vibration transitions form a band. So, the Morse potential, named after physicist Philip M. Morse, is a convenient model for the potential energy of a diatomic molecule. So, it is better approximation for the vibrational structure of the molecule than the quantum harmonic oscillator because it explicitly includes the effect of bond breaking such as the existence of unbound states. So it also accounts for the inharmonicity of real bonds and non-zero transition probability for overtone and combination bands. So here, this is the Morse potential energy diagram. The Morse potential and harmonic oscillator, which is Morse potential, it is blue in color. Harmonic oscillator potential, it is green in color. So unlike the energy levels of the harmonic oscillator potential, which are evenly spaced by h omega, so the Morse potential level spacing decreases as the energy approaches the dissociation energy, whereas the dissociation energy dE is larger than the true energy required for the dissociation dO due to the 0 point energy of the lowest, that is vibrational quantum number V is equal to 0 vibrational level. So, the harmonic oscillator approximation is convenient to use for the diatomic molecule with quantized vibrational energy levels given by the following equation. So, which is EV per centimeter is given by mu plus half omega E. So as a more accurate description of the vibration energy is given by the anharmonic oscillator, also called as Morse potential, with the energy level EV per centimeter. Omega is equal to omega into gamma plus half minus VE XE gamma E into mu plus half raised to whole bracket square omega E YE V plus half whole raised to bracket square, etc. So where omega E is the vibrational frequency for RE, the internuclear separation, and omega E is greater than omega E into XE, which is still greater than omega E into YE. This accounts for the fact that as the vibrational state deviate from the perfectly parabolic shape, the level converge with the increasing quantum number. It is because of the anharmonicity that the overtone occurs. So while it may be seen that harmonic oscillator and anharmonic oscillators are closely related, in fact it is not the case. The difference in the wave functions lead to the breakdown of the selection rule. So specifically for harmonic oscillator, delta V will be equal to plus or minus 1 selection rule, which cannot be applied, and a higher order cannot be accounted in the energy calculations. So, from the ground state to the first excited state for anharmonic correction, but it becomes much larger for a more highly excited state, which are populated as the temperature increases. The deviation from the harmonic oscillator to anharmonic oscillator results in the expanding of the energy function with additional terms and treating these terms with the progression theory. This results in the correct vibrational energies and also relaxes the selection rules. A delta V is equal to plus or minus 1 is still most predominant. However, weaker overtones with delta V is equal to plus or minus 2, plus or minus 3 can also occur. It should be noted that delta V is equal to 2 transition does not occur at the twice the frequency, the fundamental transition, but at these are the potential energy diagrams for vibrating diatomic molecules. So which you can see here, V is equal to 0. So this is 0 to 1. So V is equal to 1. This is 0 to 2. So this is 0 to 1. This is 0 to 2. And this is 0 to 3. This is 0 to 4. So whereas for this it is 1 to 2, 1 to 3, 1 to 4 like that. So for fundamental vibration frequencies of a molecule corresponding to the transitions from V0 to V1, for non-linear molecule there will be 3n-6 where n is the number of atoms, the number of vibrations. The same holds true for linear molecules. However, the equation 3n-5 is used because the linear molecule has 1 less rotational degrees of freedom. So following figure shows the diagram for vibrating diatomic molecule. The level donated by the vibrational quantum number V represents and the potential energy for harmonic or quadratic oscillator. The transition 0 is to 1 is a fundamental transition, whereas 0 to 1 where n is greater than 1 and they are called by the term overtones, and the transition 1 is to 1 n is smaller than 1 are called as hot bands. So overtones occur when a vibrational mode is excited from 0 to V0 to V2, which is called as a first overtone, and V0 to V3, this is the second overtone. The fundamental transitions V is equal to plus or minus 1 are the most common occurring, and probability of overtone rapidly decreases as V is equal to plus or minus 1 increases. Based on the harmonic oscillator approximation, the energy of the overtone transition will be about n times the fundamental vibration associated with a particular transition. The N-harmonic oscillator calculations shows that overtones are usually less than the multiple of the fundamental frequency. Therefore, overtones are generally not detected in larger molecules. So, hot bands are observed when already excited vibration is further excited. So, for example, V1 to V1 dash transition correspond to hot band in the IR spectrum. These transitions are temperature dependent with the lower sign intensity at lower temperature, higher signal intensity at higher temperature. This is because at room temperature only the ground state is highest populated, where kT will be equal to 200 per centimeter based on Boltzmann distribution. The Maxwell distribution law states that if the molecules have a thermal equilibrium occupied two states of energy, sigma 1 sigma I, then the relative populations of the molecule occupying these states is given by this expression. So in the harmonic oscillator model, the hot bands are not easily distinguished from the fundamental transitions because the energy levels are equally spaced. Because the spacing between the energy levels in the N-harmonic oscillator decrease with the increase in the vibrational level, the hot band occur at a lower frequency than the fundamentals. Also, the transition moment integrals are also slightly different, since the ground state will not necessarily be totally symmetric, since it is not in V is equal to 0. So in the simplest cases, the part of the infrared spectrum involving the vibrational transitions with the same rotational quantum number delta J is equal to 0 in the ground state and in the excited state are called as Q branch. On the high frequency side of the Q branch, the energy of the rotational transitions is added to the energy of the vibrational transition. This is also known as R branch of the spectrum for delta J is equal to +1. The P branch for delta J is equal to -1 lies on the lower wave number since of the Q branch. The appearance of the R branch is very similar to the appearance of the pure rotation spectrum, and the R branch appears nearly to the mirror image of the R branch. So this is the rotational vibration spectrum of carbon monoxide molecule. This is the P branch and this is the R branch, which is given by the fundamental frequency, transition absorbed, fraction absorbed against the wave number. Thank you. Thank you, one and all.